Welcome to the Puzzle of the Week series. I am Łukasz, and today we'll be performing numeric operations on double types. We're adding 0.125 8 times, and because of that we're expecting the result 1.0. So let's run the test and check if it fits to our expectations. As you can see, test passed. Now let's make a little modification. So instead of adding 0.125, let's start adding 0.2. And in such case, we're expecting the result 1.6. So let's rerun the test. As you can see, this time test failed. And in the result, we received the number slightly below 1.6. To understand what happened here, we need to discuss how doubles are represented in Java. In Java, doubles are represented according to the IEEE 754 standard for floating point arithmetic. This representation consists of three parts. The sign bit, which indicates whether the number is positive or negative. A 0 signifies a positive number, while a 1 indicates a negative number. Second part is the exponent, which is expressed using 11 bits and represents the scale or magnitude of a given number. To handle both positive and negative values, the representation is biased by 1023. To obtain the actual value of an exponent, we must subtract this bias. The last part is mantissa, which is expressed using 52 bits and contains the precision or fractional part of the number. At the first glance, the theory might appear to be challenging, but it becomes simpler when we examine it in practice. Let's begin with the number 0.125 and an algorithm to represent it as a double number. In the first step, we need to encode the number in binary. During this step, we multiply the fractional part by 2 and record the integer part of the result. We repeat this procedure until we encounter a repeating sequence or until we exceed the number of mantissa bits, starting from the first occurrence of 1. So in our example, we start with 0.125 times 2 is 0.25, so we record 0 in this case. Next, 0.25 times 2 is 0.5, so we record 0 again. And in the third step, 0.5 times 2 is 1.0, so this time we record 1. And if we continue this procedure, we will observe a recurring sequence of zeros. After encoding in binary, we move to a normalization phase, where we shift the binary point to the right until there's only one non-zero digit to the left of the point. In our case, this requires shifting it by about 3 positions. With the normalization done, we can calculate the exponent. Since we shifted a fraction 3 positions to the right, the exponent is minus 3. But before encoding this value, we add a bias of 1023. This gives us an encoded exponent of 1020. Next, we calculate the mantissa, which consists of 52 zeros, because after normalization, there are only zeros to the right of the binary point. To determine the sign bit, if the number is positive, it will be 0. In the final step, we concatenate the previously calculated parts to obtain the final result. Now let's apply the same process to the number 0.2. During encoding, we encounter the repeating sequence of 0011 0011. In the normalization step, we shift the binary point again 3 positions to the right, resulting in the same exponent, 1020. The mantissa carries digits to the right of the binary point after normalization, forming a recurring sequence of 1001, rounded to 52 bits. So, as you can see, we have a slight loss of precision here. Since the value is positive, the sign bit is set to 0. In the final step, we combine the previously calculated parts to obtain the result. The purpose why we explored those two examples was to show that while some values are easily represented in the decimal system, they may not be as straightforward in double representation. The same is true when performing double operations, as we often need to round the result to the closest representation of mantissa bits. During those operations, we can lose a portion of precision that makes a significant difference. And this is the reason why our test is failing. Okay, now let's think how we can handle it. First, what we can do here is to accept a potential precision loss. It appears that JUnit has dedicated assertion for a doubles, where we can pass third parameter delta, which is a maximum delta between expected and actual value. So let's place a small value here for which we can afford. As you can see, this time test passed. If we cannot afford for any precision loss, we can use big decimals. So let's rework our code for it. As you can see, in this case, test is also working. The question is, which approach should we use? The answer depends on the situation. Typically, if you can tolerate a slight loss of accuracy, you should choose doubles because they offer better performance. However, when any loss of precision is unacceptable, which is common for example in finance operations, then use big decimals. Today we delved into the details of the double data type. We discovered that doubles follow the IEEE 754 standard for floating point arithmetic. Additionally, we discussed how when performing numerical operations with doubles, inaccuracies may arise, and we have two options to address them. Either accept a certain level of tolerance, or use big decimal instead. That wraps up our session for today. See you next week.